How do you know that the structure you are analyzing is determinate or indeterminate? The key here is in equilibrium. So you need to know the number of unknowns from your structure and versus that with the number of equilibrium conditions that you can establish. So if you can solve all the unknowns using equilibrium conditions, then the structure is classified as determinate structure. If you cannot, then the structure is indeterminate. So why do we want to have indeterminate structure? So let me use these two structures as an example. On the left is a simply supported structure, which is determinate. On the right is a climb beam, which is indeterminate. Subject them to the same loading, the uniform distributed loads. Then you'll see that the displacements of the determinate structure is about 5 times of that of the indeterminate structure. Also, the stress of the determinate structure is about 3 times of that of the indeterminate structure. So we can see that the indeterminate structure offers the advantage of smaller stresses as well as smaller deflections. Also, another important advantage of indeterminate structure is the failsafe condition. So this is a frame structure, indeterminate. So we know that if one of the columns is damaged, then the structure will still stand. Will still stand to resist the loading that imposed. One example is the 1995 Oklahoma City bombing. So one building has been damaged. About 1/3 of the building has been damaged by the bombing, but the remaining part of the structure still stands, which can provide a safe shelter for residents inside the building. However, the indeterminate structure do come with some sort of disadvantage. One disadvantage is if you have support settlements, then indeterminate structure is going to cause additional stress inside the structure. For instance, this is a beam resting on 3 supports. If I have an internal hinge right in the middle of the support, then this structure is determinate. So if the middle support have a settlement vertically downward, then you will see that because this is a determinate structure, so the deformations of the structure is more like a rigid body, and it doesn't cause any additional bending moment or stresses inside the structure. On the other hand, if you have a continuous beam sitting on against 3 supports, if the middle support again subjected to same settlements, you will see that because of the continuities of the beam, you're going to see the beams is going through some sort of curvature, which indicating that inside this beam, you are going to see bending moment as well as stresses induced because of the settlement. Also, if you have temperature change for the components, if the component is determinate, they are free to expand or contract, then you are not going to see any stresses caused by this temperature change. But on the other hand, if you have an indeterminate structure, such as this climb beam, if you have a temperature change inside the component, because the component has been refrained from expansions, so you're going to see thermal stress induced inside this indeterminate beam. Because the indeterminate structure offers a very good advantage, smaller stress, smaller deformations, and fail-safe conditions. So most of the structures that you see, they are indeterminate structure. So analyzing these indeterminate structures remain a very demanding task. If you are fortunate that the structure you are analyzing is a symmetrical structure, then you can use the following concepts to simplify your analysis. First, we need to define what is a symmetrical structure. To be called a symmetrical structure, you have to find an axis of symmetry. And when you do reflections of the structures with respect to the axis of symmetry, the structure remains the same. To be a symmetrical structure, the structure has to be identical in terms of geometry, support, as well as material properties. So here are some examples of symmetrical structure. So take a look at the first structure. So the structure is a beam sitting on 3 supports. At both ends, they are roller support. At the midpoint is a hinge support. They have the equal length and the same properties on both sides. So we identify that vertical axis at the midpoint there is the axis of symmetry. So if we do a reflection with respect to the axis of symmetry, the structure remains identical. So we call this structure symmetrical structure. So the same thing goes for the other 2 structures. They are also symmetrical structures. Sometimes we can relax the conditions a little bit. For instance, this is a beam sitting on 4 supports. On the left is a hinge support, and the remaining 3 are roller supports. So they have 3 spans. The 2 spans at the sides, they have equal length. The properties are exactly identical. Because the hinge support and the roller support, so strictly speaking, this structure is not a symmetrical structure. However, if you realize that they are only vertical loads, no horizontal force. So horizontal loading at the support A is going to be equal to 0. So when you do reflections of the structure with respect to the middle axis, you'll find out that the hinge support now goes to the right, the roller support goes to the left, but the hinge support, the actual forces of the hinge support is 0, so it tells you that the structure remains the same as before, so we can still loosely call this structure a symmetrical structure. Now, after defining a symmetrical structure, we can also do the same definitions for loading. So loading also have a very similar properties. So we call the loading symmetrical if we can identify an axis of symmetry, and if we do a reflections of the loading with respect to the axis of symmetry, the loading remains the same, then we call this set of loading symmetrical loading. And here are some examples of the symmetrical loadings. So this is a triangle loads on both sides, and we identify axis of symmetry at the midpoint, do reflections, and then the loading remains the same. So we call this symmetrical loading. So the rest of the 2 cases are similar. Now, another type of loading we call anti-symmetrical loadings. So if the set of loading remains the same after we do a reflection with respect to our axis of symmetry and then do a negative signs on this reflection, they go back to the original loading conditions, then we call this anti-symmetrical loading. So here is another example of anti-symmetrical loading. So first you do a reflection with respect to axis of symmetry, and then you do a negative on the reflected image. If the loading goes back to the original loading, then we call this anti-symmetrical loading. So why do we introduce symmetrical loading and anti-symmetrical loadings? The reason for that is we can always decompose a set of loadings into a summations of symmetrical loads and anti-symmetrical loads. Let me show you how we can do this. For example, I have this given set of loading, which is easily seen is not symmetrical nor anti-symmetrical. So I have a 20 kilonewton per meter on the left span and 30 kilonewton per meter on the right span. And somewhere in the middle 2 spans, I have 50 kilonewtons concentrate loads. So I can take this loading, divide it by 2, scale by 2. I call this B. And I do a reflections of B. I call this C. And I can sum B and C up, which give me a symmetrical loading. I can take B, subtracted C. Then you can see that this gives me an anti-symmetrical loading. So if I take these two loadings, sum up, become 2B. So 2B is equal to A. So symmetrical loading plus anti-symmetrical loading equal to the original general loading. So this just shows me a way to decompose a general set of loading into a summations of symmetrical loads and anti-symmetrical loads. So this is another example to decompose a general set of loading into a summations of symmetrical loads and anti-symmetrical loads. So first I take the loading divided by 2 and then do reflections respect to axis of symmetry. Summations of these two cases give me a symmetrical load. Subtractions of these two cases give me an anti-symmetrical load. And again, the summations of symmetrical loads and anti-symmetrical loads give me the original general loading. So why do we want to decompose loading into symmetrical and anti-symmetrical load? It so happens that if you are analyzing a symmetrical structure, you can utilize these symmetrical and anti-symmetrical decompositions of loading to simplify your analysis. So assuming that I have a symmetrical structure and I want to analyze the response of the structure under loading, I can directly take the loading, apply onto the symmetrical structure, and analyze. Or I can decompose the loading into symmetrical loads and anti-symmetrical loads, and then do two separate analyses. So I do symmetrical loads on symmetrical structure and then get the first response. Then I do anti-symmetrical loads on symmetrical structure, get the second response. And according to superposition principle, the response, the first response and the second response summation should be the same as the response that we are looking for. So you can utilize this symmetry and anti-symmetry loading conditions on the symmetrical structures to simplify your analysis. So let me show you this concept. So this is a beam sitting on a hinge support. So apparently this is a symmetrical structure. So applied two concentrate loads located at A away from the N. So the loading is symmetrical. So this is a symmetrical load acting on symmetrical structure. So you can anticipate that because of the loading symmetry as well as the structure is symmetrical, so the deformations of the structure is going to be symmetrical as well. So that is to say that you can do a reflection with respect to the axis of symmetry, which is at the mid-vertical axis here. If you do a reflection of the deformation, it's going to be identical. So because of that, then we know that the slope at the midpoint has to be equal to 0. But on the other hand, of course, because of the curvature, then you are going to have bending moment, and you are going to see a vertical displacement at the midpoint as well. So instead of analyzing the whole beam, you can just cut the structure in half and then analyze just half of the structure, imposing a proper boundary conditions to reflect that you just have observed from the symmetry conditions. So the midpoint here is going to go through a vertical displacement without any slope, and it has to come with a bending moment. So this is the corresponding boundary condition under such a symmetry condition. So instead of analyzing the whole structure, you can only analyze half of the structure and then do a reflections of your results. Then you have the whole beam's results. So this is the conditions of symmetrical loads acting on symmetrical structure. Now, the other condition is if I have a symmetrical structure, but the loading is anti-symmetrical, such as this. So I have a concentrated load on the left pointing downward and concentrated load on the right pointing upward. So this is a symmetrical structure, and because of these loading conditions, you can anticipate that the deformation is going to be anti-symmetrical. So which means that if you do a reflection respect to the axis of symmetry and then do a negative sign change of the deformations, then you're going to have the same deformations. So because of that, then we can identify that the midpoint, you're going to have displacement at the midpoint, but the slope is not going to be equal to 0. Also, because of these anti-symmetrical deformations, the curvature on the left is going to be positive, and curvature on the right is going to be negative. So they meet at the midpoint, which give you 0 curvature. So it's telling you that at the midpoint, the bending moment should be equal to 0. So conclusion, the midpoint there should have slope, but the moment and vertical displacement should be both equal to 0. So as a result, you can impose such a boundary conditions onto the left side or the right side of the beam and analyze just half of the beam. So the corresponding boundary conditions for the conditions that we just mentioned is actually a hinge support. So hinge support, you don't have displacement, but you do have slope, and you don't have bending moment as well. So you can just analyze this part of the structures and then do an anti-symmetrical mapping to the other sides of the beam. Then you have the results for the whole beam. So this is a condition for symmetrical structure under anti-symmetrical loads.